Okay, so we are back into recording mode. I don't know if anyone, I didn't, of course, listen to the video myself, so I'm hoping this is helping those that cannot attend, but this is the best I can do. Right, so we're going to finish hopefully by the end of today, we'll finish our discussion on ideal flows. Just again, I'm hammering down, but ideal flows are flows which are irrotationals and incompressible. Right? And so irrotational, that allows you to assume that your flow velocity field derives from a potential. So you can write the velocity field u as the gradient of a function. And if you add on top of that incompressibility, which is essentially what we always assume in IFD, then the potential satisfies the Laplace equation, and it allows us to use a lot of analytical tools, a lot of mathematical tricks in order to compute flow fields and pressure fields easily. Now, the last topic we introduced on Tuesday were complex flows, and that is a way of representing so this is not a new concept in terms of the physics of what's happening in the flow. This is still an ideal flow. So we still have the basic building blocks that we had before, uniform flows, sources, sinks, dipoles, irrotational vortices. But it introduces a new mathematical formalism that actually allows you to simplify the mathematics. Right? This is, of course, always assuming, which in most textbooks still assumes that that people are still very much used to using complex numbers, which is a bit less the case. People are much more familiar now with numerical tools and using MATLAB than complex numbers. Right? I would say that maybe 60 years ago, complex numbers were the equivalent of MATLAB. It allowed you to do much more, represent flows in a way which was analytically and in terms of computation easier. But now I think people will turn to computers. Nevertheless, it still gives you a lot of insight into the flows. So for this whole part, what you have to remember is just that whenever you see a function of z, you can differentiate it and you can use it just like real functions. Right? So even if you don't have, say, the mathematical background about complex analysis, it doesn't matter. For everything we'll do in this class, every time you see a function of z, just differentiate it the way you did for functions of the real variable. And remember that when you have a potential, then so let me just write that down. Right, so our complex potential, the things you have to remember is that the real part of the complex potential is the same function as the potential we discussed before. So if you took the gradient of this function, you would get the velocity field. And the imaginary part happens to be the stream function. So if you take you take the imaginary part of that function, that is your stream function. So if you take that stream function equals to a constant, all of the points which are going to satisfy, which are going to be on the same contour, they will be streamlines. Okay. And then the equivalent of the gradient is just the regular derivative. So if you differentiate omega z as a function of z, and this is similar to what you do when you take the gradient, and what you get is the velocity field, except that the real part is the u component, the x component of the velocity, but the imaginary part is minus the y component of the velocity. That's the only trick you have to remember. Okay, so with that, we took a few examples. So we looked at the flow induced by an irrotational vortex close to a wall. So that we did. And now what we are going to do was to do what should have been the first example, but ended up being the one we will do now, because I thought we didn't have time to do it. So let me just find it back into my notes. I have to go back in time. And where is it? We will redo the so here it is. We will redo, I think this is, no, I forgot my numbering. Can anyone remind me what my numbering is? 4? Okay, this is 4 dot into chapter 5, I think, yeah? 5 was complex potential, and then there was 1, 2, 3.
Yeah, 5 is 5. Like compass.
Yeah.
This is 3.
3. Okay. Oh, 3b. Okay, this is all getting very involved. Problem is I'm not following my notes, so at some point the numbers don't match and then it becomes complicated. Okay, so what we'll do is we will redo the flow around a cylinder. Okay. So it's the same problem that we did before with real. So you'll see it's the exact same motion. So if you want to create the flow around the cylinder, let me remind you of that. So we have a cylinder. Now, again, we're really in that little part, and you will change in the second hour. But we're just discussing 2D planar flows. So complex potentials is only for 2D planar flows. Then we have the flow around the cylinder. We may have like an incoming flow, say U. Now, actually, that would be already in real, for real potentials a bit more difficult. But let's assume that we actually have a flow which is coming at an angle, right? Because you'll see that in complex potential, it's easy. If you did it for real potentials, it will be already a bit tougher. It will be not very tough, but the formalism will become a bit more tricky. Okay, and we have a cylinder. So how do we solve that? And we say we want to compute the flow. Say the question is, for instance, compute the lift or compute the pressure distribution. In that case, you need to compute first the flow, and then from Bernoulli you can extract the pressure, integrate the pressure, so integrate the stress vector along the surface, and you get the forces. Right? So let's start with the velocity field. We want to compute the velocity field. Now you know that this is an ideal flow, so you can construct the velocity field by superposing certain particular flows. Right? We have at our disposition, we have uniform flows, we have sources, sinks, dipoles, irrotational vortices. Those are essentially the building blocks of any potential flow. So for the flow around the cylinder, you already know, we've already discussed. So that part is the same as what we did before. You already discussed the flows we have to add. We have to add a uniform flow, and we have to put a dipole at the center of the cylinder, and we have to put an irrotational vortex at the center of the cylinder. Yeah, remember that? So we'll do this, but using complex potentials. So now this is my complex potential. This is the complex potential for the flow representing the flow around the cylinder. And so to build that, we have to put first a uniform flow. Now remember, we discussed the equivalence. So the uniform flow now, the potential is just a complex number times z, and that complex number represents the uniform flow. Now we discussed it last time already. For potential flows, when you go to infinity, essentially, when r goes to infinity, we already know that. Right. Our velocity, the velocity field, this is our boundary condition at infinity, will be our vector u, right? This is what it will be at infinity. So we'll write it directly. I just make a shortcut. Otherwise, I introduce notations which are purposeless. So we know that the flow at infinity will be essentially our uniform flow. The flow induced by the dipole and the flow induced by the irrotational vortex goes to 0 at infinity. So the only part you're left with is the uniform flow. So this one you have to match with your boundary condition at infinity. And so the boundary condition at infinity will be a number, a complex number, and this number is going to be our uniform flow times z, right? Remember that this minus I alpha is here only because, let me just do that real quick. If you took if you want to see what the velocity field associated with that looks like, you have to differentiate your potential. So when you differentiate u exponential minus I alpha z, well, you differentiate this just like a function of the real variable, so that the derivative of z is just 1. You end up with this, right? And this is equal to u times cosine alpha plus, or actually I should write minus, right? Minus I u times sine alpha. This minus sign here comes from, let me use a bigger pointer. This minus sign here comes from the fact that I have a minus alpha. Right? And so since I know that this is u minus I v, you can directly identify this to be v and this to be u, and this indeed corresponds to this flow here. Right? So this flow here, u with an angle of alpha, the x component is u cosine alpha, and the y component is u sine alpha. Okay? So this is why you have this minus alpha here. All right, so this is the first part of our potential. Now we have to add the potential generated by a dipole. So d divided by 2 pi z. This is, let me just write it underneath here. This is potential associated with a uniform flow. This here is the potential of our dipole. Now it is important to note that this represents your dipolar moment, d. Oh, sorry, I'm going to use that, d. And this d is a complex number. So just to reinforce that, I'm going to put a little tilde on top, and know that so this is not just a real number. It has a real part in general. Right? It could be just a real number, and you'll see this is the case when actually alpha is equal to 0. But it could have a direction. Right? So it has a real part and a complex part in the general sense. So d is a complex number. Huh? So d is in C, not in R. This is our potential associated with the dipole, and the last thing we have to add is our irrotational vortex. And if you go back to your notes, the potential associated with an irrotational vortex is I divided by gamma times gamma divided by 2 pi. Hold on. So for the number that has just no real component and one as an imaginary component, you guys use I, right? Because some people sometimes use J. I think electrical engineers use J, but this is fine. So I here really means just the pure imaginary number. The number whose square is equal to -1. Yeah. So this is I gamma divided by 2 pi times 1 divided by z. So you did the same step. It's exactly the same as with real potentials. You constructed your complex potential, and now you have to impose your boundary condition. So we imposed our boundary condition at infinity already by writing that a uniform flow is this, and we need to impose a boundary condition at the surface of the cylinder to identify d. And just like, no surprises, of course, just like what we had for real potentials, gamma, the circulation, will remain undetermined, right? Which means that we can have a solution to that problem with any value of gamma. So now the question is, how would you impose the boundary condition? What boundary condition do we impose? No penetration. So how would you do that? So now, boundary condition that we need to impose, we need to impose the no penetration boundary condition. Where do you impose that? Where? At R equals A. Yeah, I can't see who is talking actually. So this was you. Okay, this is why I kept looking. Yeah, exactly. So again, also back to your exam, whose grades will be posted probably today or tomorrow. when you impose a boundary condition, sometimes you get confused. You write the right boundary condition, but then you forget to write it at the right place. Right? So you don't write that the no penetration boundary condition. You will write u dot n, right? In this case, equals to 0, but it's not your general velocity field dot n, which is equal to 0. It's your velocity field at your velocity vector at the boundary. Right, so don't forget, so u here, assuming u is a function of r and theta, it's not u and r and theta, it's u at really a, and for any value of theta, dot n, which is equal to 0. So if you still have r's floating at this point, you have a problem. Right? Of course, you have to replace this boundary condition you're writing at the boundary. Right, so if, for instance, you are writing a boundary condition at a wall, say this is my wall. Okay, this wall is clearly determined by y equals 0. If when you write your velocity field, you still have y's floating, then you have a problem because you're not at your boundary. You impose the boundary condition at the boundary. Yeah? Don't forget that. That was the parenthesis. So no penetration boundary condition, so you're writing that the velocity field u at, I'm going to write this, r equals a, and your boundary here is determined by r equals a, but it's the whole cylinder, so theta is any value of theta between 0 and 2 pi, and theta dot n equals to 0. Right? That would be the logical route to follow. I think you said that, so what would you do next? So you have to get to u. So the first method, we'll follow the second method, but let's just discuss the first method, which is always a possibility. So you want to get to u, right? So how do you get that? How do you get to the velocity field? You differentiate the potential. Huh? So you continue what we did here. So here I only did for the velocity field, but you differentiate the potential. You differentiate your potential. So I'll do this here. So when you differentiate the uniform flow, you get u, the norm of u, the modulus of u, exponential minus I alpha. Z becomes just 1. And then you differentiate 1 over z. So what do you think you get? You get minus 1 over z squared. Yeah? So remember, for function of the complex variable, just differentiate that exactly the same way you did for real functions. And for... Hold on, I did a mistake here. It was log, eh? You should have stopped me. It's I gamma. The potential is I gamma log of z. Yeah? Who picked on that and didn't tell me? Okay. Yeah, you should have spoken up, eh? Yeah. It's your fault. No. Okay. So it's plus I. Go back to your note. I wrote the... Yeah. You're right. There should be a minus in front of the I. Yeah. Well, that's the thing. Yes and no, because yes, there should be a minus, but because we're gonna, when I write for a cylinder, in a way, this is the only case where I put myself into the mind of an aerodynamicist, right? And in their mind, gamma is positive in this direction, and it's a very simple reason. It's because u is always going to be, let me use the board. You're always going to pick u positive in this direction, right? And you have a cylinder, and you want lift to be in the positive directions. So you want your lift to be a positive number, and it's going to be a positive number if gamma is positive in this direction. So this is the only reason why they always pick gamma positive, right? Because otherwise you have to, if you want gamma positive in this direction, then you need u positive in this direction, but then u is negative, which is weird. Yeah. So this is why. So in that case, actually, let me just put a note of that on that. So here, yeah. For For all airfoils. Yeah, whenever you compute, so in thin profile theory, every time you have an airfoil, and then you count the bound vorticity. This is how they compute it. You count it positive anti-clockwise, when usually mathematically you would count everything positive anti-clockwise, right? So in airfoil theory, gamma, when you discuss circulation, gamma is positive in the clockwise direction, usually. Right now, I cannot. Maybe in a few countries it's different, but in many countries, and I think in most of the textbooks in aerodynamics, gamma would be the circulation around an airfoil or around a profile would be counted positive clockwise. Yeah. So let me just put a note here. Here, this is with aerodynamics conventions of U positive and gamma positive in the clockwise direction. Okay? Circulation positive in clockwise direction. Because then you have a positive lift. Okay, so let me continue. So when I compute the velocity field, then it becomes 1 over 2 pi, and the derivative of L log of z, natural log of z, is 1 over z. Again, exactly, everything is exactly the same way. Now I would have to take the real part and the imaginary part. So here that would become a bit more tricky, but it's still very doable. So remember that this here is u minus iv. So you would have to take u minus iv, and then in a way you have to dot with the normal vector. Okay. So actually I'm not going to do that, but you should definitely do it. It will give you some practice with complex numbers. And so my question to you in particular is, so let's do, this is a question. How would you write u dot n, but n here is really the unit vector pointing in the radial direction. How would you write u dot n with complex numbers? How would you do that? Because this is essentially what you have to do. So I encourage you to, as soon as you're out of this room, to just try it. This is great fun. So u dot n, you will have to impose this is equal to 0. And then once you've done that, once you've written u dot r with complex numbers, then you can write u dot r equals 0. And then you have the exact same answer as what we had before. So this is the first method. And if there is a first one, of course, there is a second one, and that one, this is the one that we'll do. So who has an idea on how you could impose this boundary condition in a slightly different way? It's the exact same boundary condition, but really using to its full potential, the complex potential. Right? So remember, when you write your complex potential, you have two things in one. You have the potential, and you have the stream function. So how would you, yes. Not 0, but constant where? At the boundary, right? So if you make sure that your cylinder is a streamline, then you impose a no-slip in the no-penetration boundary condition. Yeah? So the other method is just to write directly. So the second method if you want, it's not an official method, it's just a way of doing it. It's just to impose that the boundary of the cylinder is a streamline, right? If you impose that a boundary is a streamline, then you essentially impose a no penetration boundary condition on that line. So if the boundary of the cylinder is a streamline, the way you can write it into the stream function is just to write that your stream function psi at r equals a, and for any theta, is equal to a constant. If you have that, then this is another way of writing the no penetration boundary condition at the surface of the cylinder. Let me write that. This is equivalent to no penetration boundary condition at the surface of the cylinder. So let me rewrite our complex potential. So here I don't even have to differentiate my complex potential. I just rewrite my complex. I just rewrite it. I'm going to rewrite it as that. So u exponential minus I alpha. To avoid writing twice the same thing, what I will do is I will directly write that z is equal to r, write it with modulus and argument. My complex number z, I'm going to write directly in that form, r e exponential I, theta. R is the modulus, so the distance from the origin. Theta is the argument, so the angle from the x-axis. Okay? So I'm going to replace all of my z's by that, which will make it easier. R e theta plus my complex d divided by 2 pi z, and z is r exponential I theta, plus, because we are in aerodynamics convention, I gamma divided by 2 pi times the natural log of z, and again I'm going to write z as r e theta. Now I'm just going to write an intermediate step to make everything clear. I'll put all the moduli together. Sorry. And I'll put all of the arguments together. So this is u r exponential I theta minus alpha plus 1 over 2 pi. Now I'm going to write d. I'm going to express now d, my dipolar moment, in its modulus and argument form. So let me call d with no tilde the modulus, and exponential I, any Greek letter for the angle, well, delta, because then I have d's everywhere. So delta is going to be the angle, and I have 1 over r, and 1 over exponential I theta is exponential minus I theta. So then I have a minus theta here. Okay? This minus theta is just this minus theta here just comes from the 1 over exponential I theta, and then plus I gamma times 2 pi and this is the log of r plus I theta. Sorry, yeah, yes, yeah, plus I theta, yeah. D now is real. So I'm just, let me make that very clear. Just because D is essentially what I'm going to solve for. So, and D is a complex number, so instead of writing capital D, or instead of writing it in with its real part and its imaginary part, I represent D with its modulus and its argument. Right? That's why you have this delta. All right, and now what do I have to do? I have to take the imaginary part, because the imaginary part is my stream function. So we'll take the imaginary part of this. So the imaginary part of W is equal to my stream function, so this is what I want, and this is equal to, So u times r times sine theta minus alpha plus d divided by 2 pi r times sine of delta minus theta plus gamma divided by 2 pi log of r. Okay, so this is my my stream function. So once you've written the potential, you just take at that point the imaginary part, and now we just write that our stream function on our surface, so at r equals a, and theta has to be equal to a constant. So we have that u a sine theta minus alpha, theta can still float between 0 and 2 pi, divided by 2d 2 pi a sine delta minus theta plus gamma divided by 2 pi log of a needs to be equal to a constant. Now note, as expected from what we've seen before, we already know that for the irrotational vortices, this is not a problem. Right? The streamlines of just an irrotational vortex are circles anyway. So you see here, you have a constant equal to a constant. So this is, you don't need to fit anything there. Gamma is still going to remain undetermined. Now the only place where you have to fit, of course, is this has to be a constant, and this is not a constant because theta can float between 0 and 2 pi. So you need to make sure those two things cancel, and the only way for these things to cancel is for delta to be equal to alpha. Right? You have the sum of two signs. They need to have the same phase, because otherwise you can't cancel them. They just have two signs. So the only way you can do that is, so this is going to be a constant only if you have alpha equals to, delta equals to alpha. And once delta is equal to alpha, you still have a sign, right? So you need to have the constant in the front equal to 0. Yeah. So you need to have u times a minus d divided by 2 pi a. This needs to be equal to 0. And then those two terms cancel, and then you're fine. Right? So for this to be equal to a constant, that whole part here needs to be equal to 0. Huh? Maybe I should have written that. This has to be equal to 0. So how do you write that? So let's write, let me do this again. Okay. So this here needs to be equal to 0. And so that leads to those two things. Right? So if we want this to be equal to constant, then those two terms need to cancel each other, which leads to delta equals to alpha, and UA equals to minus D divided by 2 pi. So if you finish off that, then you see that your complex delta needs to be, here D needs to be equal to 2 pi A squared U exponential I delta, I alpha. Okay? Okay. So the 2 pi A squared U, this is what we got before, when alpha was equal to 0. So if you go back to your notes for a cylinder, we identify the value of the dipole. Yeah?
Why is there a minus between U, A, and B plus
So because if you, so here, see here, you have to, so you need to make sure your two signs have the same phase. Right? So you agree that delta has to be equal to alpha. So here, once you put an alpha here, sine alpha minus theta is minus sine theta minus alpha. right? So then it becomes UA minus D divided by 2 pi A. If you rewrite this, I can rewrite that. So this becomes U A. So if I have a delta here and delta is equal to alpha, then UA, I have UA minus D divided by 2 pi A sinus theta minus alpha is equal to 0. Right? Once you've identified the phase, then this needs to be equal to 0, so that needs to be, this thing here needs to be equal to 0. Okay, so this is, this is an example for, so of course it's the first time you play with complex numbers in that way, so it may not seem simple, but it's actually, in terms of analytics, it is simpler. But again, you're still completely free to use the real potentials. You could do the same thing with the real potentials. Now the third, this is now B, so now we're going to go to C. And the last thing we're going to look at is the flow around corners. Now to be honest, the flow around corners, again, you could do that with real potentials, but that would be now extremely tiresome to do this with real potentials. Here, like definitely complex potentials beat real potentials. So this is our last example, and this will be the flow in corners, corner flows. See, corner flows, and those are flows which are only, usually you will only, when you look at these flows, you only need to focus on the corner, because what is happening at infinity is not very physical, okay? But those are the flows which corresponds to the potentials, the very first potentials we introduced, and the one which is perhaps analytically the easiest, where you would just have a constant, and it really doesn't matter what value this constant is, times a monomial of the function z. So let's take this potential here, and let's think about what this potential represents. Okay. So the easiest way to think about what this potential represents is to look at the streamlines. So we'll directly jump to the stream function. So let's look at streamlines. So for that we have to go to the imaginary part. We take the imaginary part of a complex number, and again I will represent z by its modulus and its argument. So then my complex potential is equal to C0 z to the power n, so it's just a constant, r to the power n exponential I n theta. Now don't look at the modulus, the important part here is to look at the argument, so at this n at this n theta here. So when we take the imaginary part, so our stream function is going to be equal to the imaginary part, which is just C0 r to the power n times sine of n theta. Okay? Now when you have a sine of n theta, let's not look at r to the power of n. We want to look at streamlines. When is this here equals to a constant? Those determine streamlines. Sine n theta. You have to look at the argument. Your argument, because you're rating z to the power n, exponential of I to the theta to the power n is exponential I n theta. So when you take the imaginary part, okay, let me go back. So this is C0 r to the power n cosine n theta plus I sine n theta. Yeah? So your imaginary part here is C0, the constant, r to the power of n, times sine n theta. Yeah? Do you guys remember that exponential I alpha is equal to cosine alpha plus I sine alpha? Because I've been using that a lot. Maybe that was the piece of information which was missing. Now you remember. Yeah? Okay, so this will define a streamline. And so look, there are many ways you can make this, you can compute streamlines. So for instance, if you want, this gives you parametric, like polar equations for streamlines. All your streamlines will look like r to the power of n is equal to some constant divided by sine n theta, but this is those are complicated streamlines. R is a function of theta, but which streamlines here are simple to see? Right? Can anyone here give me one streamline? An easy one, the easiest one. Huh? No, n is not a variable. N is 1, 2, 1/2, alpha is anything. Your variable are theta and r here. This is what tells you where you are in space. Yeah? Theta equals to 0. Theta is equal to 0. If theta is equal to 0, then indeed, for any r, right, I have a constant, which is 0. Right? So here, for example, theta equals to 0. Now the line with equation, what is theta equals to 0? This is a ray going from the origin all the way to infinity. That's what theta equals to 0 is. It's a line, it's a curve. Yeah? This here, this is my plane. Then theta equals to 0 is this line. All of the points are theta, such that theta is equal to 0, lie on this line. So this here is a streamline. Now that you found one, I think it's easy to find a lot of them. So what other streamline will you find? You see on the spot. You found one. Find another one. So you simply have to think, when is sine n theta equals to 0? So when is sine n theta equals to 0? And n doesn't have to be an integer. It doesn't have to, right? If you write n theta equals to pi, or any multiple of pi, then that works. Yeah? So actually the general form would be just n theta. If this angle here is 0 pi, 2 pi, 3 pi, 4 pi, 5 pi, any of these, the sine is always going to be equal to 0. Yeah? So if n theta is equal to any k pi, where k here is an integer, so k is an integer, let me not do that, is an integer, then I have a streamline. Do you all agree? Is that clear? Yeah? So any of these will be streamlines. Now we'll finish that when we come back after our break.
Het was echt van die hemelbaan, dat je soort van omhoog heeft.
When you write the definition of omega z, it's like phi of z plus I psi of z.
Yeah.
Why phi of z and psi of z? Because z is a function of z. Inside it has I, imaginary part. So phi doesn't have any imaginary. Because when you want to say...
Phi is the... No, when you write a number, so this is... Yeah, it's complex analysis. W is a complex number. It has
Both
a real part.
and imaginary.
It has a real part.
Yeah.
And it has
Imaginary.
an imaginary part.
Which the imaginary
Phi is the real part. So phi is a real number.
Yeah. Phi is it. So can you
I
write it in the
psi-
terms of Z phi? Can you write phi?
You can, but you
But
know that
then
Z.
then you should insert some I inside Z. Because
No, you don't. So it's
Because
the only thing you need to know is that
IY.
it's a real number. So phi is a real number.
yeah.
Right now you're writing as a function of z because z is how we represent numbers.
Yeah.
But you could just as well write it. You know, this is really x plus iy, so you could just write it as a function of x and y.
Yeah,
It's
we
just
can write. Yeah.
So this is your function of x and y. When
Yeah,
you write that,
but my point
oh,
was.
hold on. Let me just stop that.
Yeah.